Hello, researchers. Welcome back. So, this is regression part two. Um, and first, let's talk about accuracy of prediction. So, we know regression is used for prediction. And so now we have a line, and it's the best line for our data, but the best line may still not be a very good one for making predictions. And so we have an example here of real gross domestic product growth and how that relates to equity return for various countries. And you see, we have a regression line, which you can also think of as a trend line, and we have an equation there up at the top. But if many points are far from the line, then our line doesn't predict very well. And so, how do we quantify that? How do we quantify this idea of how accurate our prediction might be? The way we do is, well, first of all, let's start with the standard error of the estimate. Okay, this is like the standard error of the mean, the standard deviation of the sampling distribution, but instead of each point being compared to the mean, it's each estimate being compared to the line, each point being compared to the line. So the standard error of the estimate. Since this is essentially the standard deviation around the line, the same types of conclusions can be drawn as with standard deviation, and the units are in units of y. But that's not what we usually use. We will report the standard error because it does give information. Okay, we'll report the standard error of the estimate, which is b or beta. But to what people normally use, and I'm on slide 5, what people normally use to claim that their regression model fits with the data is R squared. Now, what's R squared? You'll often see R squared reported with regression results. This is the amount of variability in Y that is explained by your equation. And the equation is called a statistical model. Okay, so you can calculate R squared simply by squaring the correlation R, lowercase r. You could also calculate it by squaring beta. This only works though if you only have one variable. And like correlation, it has no units, and this only works if you only have one predictor. So I wouldn't calculate it on your own. I get used to depending on SPSS. Like correlation, it doesn't have units. It's on a common scale from 0 to 1. So it's a standardized statistic, R squared. Okay, it's on 0 to 1. If the points are all near the line, your equation does a good job of explaining them. This is slide 6. So your R squared value will be high, and also the correlation will be high. So by high, I mean closer to 1, just like correlation. If the points are far from the line, your equation doesn't predict them very well, and the R squared value will be low. Uh, um, and by that, I mean like zero point 0.1 instead of zero point 0.9. Studies with larger sample sizes tend to have lower R squared. So you figure when there's a large sample size, there's, all these individuals with all their individual variability, and they tend to have lower R squared values than studies with smaller sample sizes. But larger sample sizes tend to do better with giving you more confidence in your results when you're doing quantitative research. Okay, so the more cases there are, the more chances there are to be different from the predicted mean if you have a larger sample size. I wouldn't reject a large sample size because of that. It's just that if you see a study and they have, over 1,000 students and their R squared isn't very high, I wouldn't, you know, think that it's a bad study as a result. Okay. So on your SPSS output, the model summary shows you the standard error of the estimate and the R square value. Shows R first and then R square. So this was for the predicting the GPA study, and that we talked about in part one. And you see the R square value is the second purple circle, and it was 0.83. So that's a high R squared. Our model explained 83% of the variability in college GPA. Okay? We were able to explain 83%, 0.831, 83% of the variability in college GPA. 83% of the variability in college GPA was explained by high school GPA. Okay? All right. So we've got our alpha. We have A, B, beta is sometimes what you use for the standardized coefficient. I think of it, I think of all of them as beta. Um, um, but you can think of it as B instead of beta. And let's talk about how, because I think the next slide goes on to another example. Yeah, let's talk about how I would write up this predicting college GPA study. So we had our data file. I saved the data file, I think, and I put it in. Where did I put it? What did I call it? Okay. See, sample size, number distribution, GPA prediction. Okay. Yeah, we want to remember the names of our files. Okay. So I'm going to double click. This is in blue is the SPSS file. One way I can open it is to double click. Okay, and the first thing we always report are the descriptive statistics. I'm not going to go through that. You all are pretty good at that. The next thing we're going to report is the correlation. Analyze, correlate, bivariate, high school GPA, and college GPA. We're using, let's see, options, exclude cases list-wise, continue. We're using the Pearson correlation coefficient. And okay. All right. The correlation between high school GPA and college GPA is 0.912. So here, let's see. The correlation between GPA and college GPA was 0.91, and I'm going to put in my parentheses my p-value. P less than 0.001. Do y'all see where I got that from? See, significance two-tailed. See that? 0.000. So I'm going to write it as less than 0.001. This strong, I can say it's strong because for education I'm looking for correlations above 0.5 for strong. This strong positive correlation suggests that no. This correlation suggests that, or you could say shows that there is a strong positive relationship between high school GPA and college GPA. Okay. Okay, but it doesn't allow us to predict, right? Because it's just correlation. Strong positive relation. Okay. So now, um, then as shown in figure some number, right? You'll name it, and that'll be your scatter plot. The relationship between high school GPA and college GPA is linear. We regressed high school GPA on college GPA. Our fitted model was predicted. You could do it. You could put a little hat over college GPA if you can figure out how to do that. Predicted, I just write predicted. College GPA equals, what were those numbers? Okay, so that was the correlation. We reported the correlation and we reported that it was strong and positive. And so now let's do the regression. Analyze, where's regression? Regression, linear. We are using high school GPA is independent to predict college GPA. That's dependent. Statistics, estimates, model fit. Model fit is what we call the R square statistic model, because we're saying how R square tells us how well our model fits the data that we have. Okay, and continue. And options, I want to make sure exclude cases listwise. Yes. Continue. And okay. Okay, so just making sure it's using high school GPA as our independent variable, dependent variable college GPA. Model summary, here's our R square, 0.831, right? Okay. The We're going to be putting some stuff before. Let's talk about in our write-up, let's talk about what the model is before we talk about how well it fit. And for that, you need to go down to the part that says coefficients. Again, the ANOVA part is more about the model overall, and the coefficients are your actual parameter estimates. And by parameter, I mean like the statistics that we're estimating. So the slope is a parameter. Okay, so high, if a 1 unit change in high school GPA is associated with about a 0.95 change in or difference in college GPA. Point equals 0.95 times college. I'm going to make this one word to show that it's the oops, 0.95 times high school. High schools are independent. I'm making it one word to show it's the variable that I'm talking about. High school GPA plus some intercept. Was the intercept positive or negative though? Let me go back. The constant or intercept was minus 0.027, which I'm going to round to minus 0.03. So minus 0.03. Okay. So so The relationship, now I'm going to be talking about the estimate. The relationship between high school GPA and college GPA is positive because 0.95 is positive and statistically significant. How do I know it's statistically significant? I'm going to show the t-value and I need to show the p-value. So let's go back to our output. Or let's go to the slide because I think I got some circles. I'm pointing. Okay. Here, let me circle this. There. Let me just grab a circle. Okay, well, let me circle. Over here, you can't see that very well. No, okay, but you see where I'm trying to point here? At the t-value is 6.277. Here it's even bigger. T for high school GPA, the row that says high school GPA, on the coefficients box, T is 6.2. I'm going to round that to 6.28. I usually go to about 2 decimal places. T equals 6.28. P equals, that says 0, 0, 0. So I'm going to write that the p-value is less than 0.01. Close paren, period. And we know the t and the p are statistics, so I'm going to italicize them. A 1 unit difference in high school GPA corresponds to a 0.95 point difference in college GPA. That's not grammatically correct. High school. Okay. For example, now I'm going to use an example. Would not need to, I did not plug in some numbers. Let's do just 2.0. I got my calculator. For example, let's see. And I want to show you what I'm doing. If we got this predicted y, right? We know that y equals 0.95 times the high school. Let's say we got one student got a 2.0 GPA, right? Minus 0.03, right? And if another student has a 3, if that's another student has a 3.0 GPA, the equation will look like this, times 3. See that? 0.95 difference. Okay? A 1 unit difference in high school GPA corresponds to a 0.95 point difference in college GPA. For example, if one student, and I like 2.0 and 3.0 because they're round numbers. had a GPA of 2.0 and another student had a GPA of 3.0 in high school, we would expect the student that when the students are in college, that when the students are in college, the student, this is turning into a lie, so long sentence, with the higher, you know what, this is turning into, when the students are, uh, we would expect that when the students are in college, let's make this super clear. They would have GPAs of, let me do the math, got my trusty calculator. So I'm going to do the 2.0 point using that equation. 0.95 times 2 equals 1.9 plus 0.0, nope, minus. It's a minus. The constant is a minus. Minus 0.03 equals 1.87. And I know I know that it's going to be 0.95 more for the student with the 3.0 GPA. But if I wanted to go through that, so I got 1.87 for this first calculation equals 1.87. How about the 3.0 GPA? The other student. Okay. Right. Calculator. So I know it's going to be 0.95 more, but I'll just go through 0.95 times 3 equals minus 0.03 equals 2.82, right? Which is what we would expect, right? That's 0.95 more than 1.87. 2.82. They would have GPAs of 1.87 and 2.82 respectively. A 1 unit, okay. That's clear, right? Notice how we're really trying to predict, okay? Because this is regression. All right, let's look at another example. Doo-doo-doo. Okay, reading among first grade students, right? So you remember this from before? So for her dissertation, Rachel Deemer studied reading achievement in dual language settings. And so let's regress fall reading scores among first graders on their spring reading scores and examine the relationship. Now, if you look at the data visually, we have this scatter plot, right? First of all, does there seem to be a relationship? Are the dots all over the place, or do they seem to be forming a somewhat coherent pattern? I would say there does seem to be a relationship. And does that relationship seem linear? I would say yes, it does. It's not very steep, but it's definitely there. So we can figure out the correlation, right? The Pearson product moment correlation is 0.70, which for education we're going to say is strong. Okay. The two variables are correlated. So let's find out the size of the effect, the size of the relationship between reading scores in the fall and reading scores in the spring. Okay, the size of the effect. So let's, or if we want to predict, then we go on to regression. Excuse me. Oh, sorry. Okay, so as you know, we go to analyze and regression, and we're doing linear regression. We move the dependent, just like I showed you with the other one, we move the dependent variable to the top box. The outcome is in the top box, and the independent variable that we're looking at is in the next box. The first output we get, you can ignore, we just check it to make sure it has the right independent variable. We get the next output, we get our R square, and we see in this case the R square was 0.9. Oh, did we report the R square on our example? Nope. Okay. Where was that R square? The R square value was 0.912. I'm just going to put 0.91, showing that our model accounted for, showing that our model explained 91% of the variability in college GPA. All right, and these are just the calculations, so those wouldn't be in my final write-up. Okay, just their results. Okay, yeah. All right, don't want to forget the R square. Okay, so there's the R square value. Then the ANOVA box gives you statistics related to your model as a whole. We're not doing analysis of variance. That's not our analysis. That's not our data analytic technique. We're doing a regression analysis. But analysis of variance information lets us know about the model as a whole, okay? Yeah, don't let that confuse you, okay? All right. Some people do put the F statistic and p-value in their notes for their table about the model results. So you'll see F statistics in write-ups about regression results. Okay, and then we have our parameter estimates. Okay, so I circle here what for our B and for our T statistics and our p-value. Okay, and so here is what how I might report this. We regress fall reading scores on spring reading scores. Our fitted model was predicted spring scores equals 189.22 plus 0.64 times fall scores. Now, in that, I wrote the alpha first, the intercept first. It's up to you. Usually the intercept should be first. Okay. The relationship between fall and spring scores was positive and statistically significant. Then I put my t-value and my p-value in parentheses because I'm showing the statistics that support that statement. A 1-point difference in fall scores corresponded to a 0.64 point difference in spring scores on average. For example, if one student scored 416 points on the fall reading test and another student scored 426 points, notice I chose two that were 10 units apart, okay? We would predict that on the spring reading test, the student with the higher fall score would score about 6 points higher than his or her peer. How did I get those 6 points higher? Well, they were 10 points different. There was a 10-point difference, right, between those two students. And we know that a 1-unit difference is a 0.6. Okay, so if I multiply 0.64 times 10, I get 6.4. Okay, which is about 6 points higher than his or her peer. That's a slightly easier way to do it than solving the equation. Okay. So in the previous example, I could have said, uh, let's see, if there were two students, if one student had a GPA of 2.0 and another student had a GPA of 4.0, we would expect that that's 2 point difference, right? And it was a 0.95 was the size of the effect. So that would be 0.95 times 2 is 1.9. We would expect that the student with the higher high school GPA would score one, have a college GPA that was 1.9 points higher than the student with the lower GPA on average in the population. All right? Okay, some language for you there. Some final points about regression. We use the language of causality, predictor, outcome, effect, but causality is determined by research design, not by analysis. The studies we've talked about in this lesson are relational but not causal. So you have to be careful of this when you're writing up your analysis. We would predict, this suggests, that kind of thing, using moderating your language, modulating your language, so that you're not saying we know for sure, okay? Because these are observational studies, these are not experimental. We cannot make those claims. Regression is one of the most useful and flexible statistical tools available. There are many different types of regression. You could spend a whole course on regression. We've just gotten a taste of it here. Um, but as you're reading, you'll see different flavors of regression reported in research articles. Many social scientists, educators, psychologists, sociologists, economists use regression in their studies, and it's been famously used to predict sports results, to predict the results of elections. It's a tool for prediction, and so it's been used in some very interesting ways. And now that you have had this lesson, you know some of the basic language that can help you understand a wide variety of research articles. Okay, I hope you have a great day. Bye.